So in this module, let's have understanding about how the BJT works. So as you can see that there are three regions called as emitter, base, and the collector. Emitter is heavily doped N-type of semiconductor. Base is P-type of semiconductor, which is lightly doped. And collector, which is N-type of semiconductor, is moderately doped. Now we see that the emitter is having a majority carriers which are electrons, base has a majority carriers which are holes, and collector has majority carriers which are electrons again. And when these PN junctions are connected, this is N and P, so that forms one junction. Let's call this junction 1. And this is another PN junction. Let's call it as junction J2. So when you have this junction form, the electrons try to diffuse from emitter to the base, and holes from the base try to diffuse to the emitter region. So this process is called as diffusion process. Because of that, the depletion regions are created across junction J1 and J2. Here also, holes from the base try to diffuse to the collector, and emitter from the collectors, the electrons from the collector try to diffuse to the base region. And here also, across junction J2, there is another region called as depletion region is formed. This process happens for a while, and after the equilibrium position is reached, what you have is a depletion region which is depleted of any charge carriers, and a built-in potential is generated across the junction J1 and J2. Now, the emitter current is composed of two components, that is IEN is due to the electrons and IEP is due to the holes. And there is this current called IB1. This is the base current, which is because of the holes traveling from the P region to the electron region, to the emitter region. That is called as the base current. Now there are two currents. One is called diffusion current and one is called drift current. So diffusion current is what I explained. The electrons, as shown by this gray shaded arrow, they try to diffuse from the emitter to the base, and the holes, they try to diffuse from the base to the emitter. So that is the diffusion current. Same happens across this junction. Your holes try to diffuse to the collector, and the electrons from the collector try to diffuse to the base region. So that's the process called diffusion current. So what happens when you apply a voltage difference across the junction J1? This is the junction J1. And what happens when you apply again a voltage difference across the junction J2? So you see the positive is connected to the P type of material, which is the base, and the negative is connected to the N type of material, which is the emitter. So what happens is that this negative potential applies a force on the electrons which are present in the emitter, and they push towards the base region. Similarly, this positive voltage applied to the base exert the force on the holes which are present in the P-type material, and they push it to the emitter region. So this current is called as IB1 due to the holes traveling from P-type material to the N-type of material, that is from base to emitter. And this current, current that is causing the electrons to travel from emitter to the base, they are coming here, is called as drift current due to the electrons, and this is due to the applied voltage. And such kind of biasing is called as forward biasing, because you connect the negative terminal to the N-type material, which is emitter, and a positive to the P-type material, which is the base. Now, what happens is that some of the electrons which have traveled from emitter to the base, they combine with the holes present in the base regions. So you see the arrow downwards here and white arrow upwards. This process is called as recombination of electrons with the holes. So some of the electrons get lost because they recombine with the holes present in the base region, but the other gets transferred to the collector region because of the applied voltage here. You see that this voltage is connected in such a way that the positive is connected to the N type of material, which is a collector, and the negative is connected to the P type material, which is the base. So what happens is that due to positive voltage applied to the collector, the electrons present in the collector and the electrons coming from emitter to the collector, they are attracted. It applies the attractive force. This positive voltage applies the attractive force and they collect the electrons to travel to the collector and out of the collector region and collect it to the positive terminal of the battery. This negative potential that is applied to the P region of the P type of semiconductor will push the electrons in the P type material which have traveled from emitter towards the collector. So there is a full current going from emitter to the collector. We have said that due to this voltage applied here, the electrons which are coming from the emitter region, some of them get recombined with the base, holes in the base, and others, they are collected across the collector region because of this voltage polarity we apply. So positive voltage at the collector makes sure the electrons experiences an attractive force and they are collected in this way. Okay, so this junction is in the reverse bias position. Across this junction J2, we apply a reverse biasing. Across this junction J1, we apply a forward biasing. So you see, we say that the base emitter junction gets forward bias and the collector base junction get reverse bias. So this is how the BJT operates. Now we have shown the direction of the charged carriers, such as electrons are flowing from emitter to the collector, and some of them get lost during the recombination process with the holes in the base region. The white arrows are showing this is the component of the hole current in the recombination process. This is the component of the hole current due to the biasing applied. So what is the conventional current direction? So when you show the electrons flowing from emitter to the collector, we say that the current is flowing from collector to the emitter. That's why I look at these arrows. We will say that the collector current flowing from collector to the emitter. We have understood that how the BJT operates, its complete working from the physics point of view. So it is called as voltage control device. Why it is called as voltage control device? Because you have a forward biasing applied here. That is a forward biasing that controls your output current. More the forward bias you applied here, there is a more injection of electrons from emitter to the base and subsequently to the collector, because the base region is just there to collect few electrons because it is quite narrow. So recombination is very low and majority of the charge carriers, that is electrons, travel from emitter to the collector. So more the forward bias you will apply, more the output current will be there. So in terms of graph, you can show it like this. You have VBE, that is a forward biasing, and you have a collector current IC. So when you apply, you start from 0 volt and apply, go up to 0.6 volts. So this junction J1 gets forward bias. So it is simply a PN junction. So up to 0.7, there is a very low current. And after that, you have a large current. That is your collector current, output current due to the applied input voltage. And here you can get the get the slope of these delta IC over delta VBE. That is called as input transconductance. Okay, so that's how you get this connection. So we say that the input voltage controls the output current, and what is that input voltage? It is your VBE, and this is called as transconductance. Transconductance. Okay, now there are two important parameters that we will define right here. One parameter is called as beta, which is called as common emitter current gain. So what is beta? It is, you can say that beta is defined as the ratio of collector current to the base current. So collector current is actually how many electrons eventually you collected or traveled from emitter to the collector. The electrons are here, and majority of them travel from emitter region to the collector when we apply a forward biasing and the reverse biasing as shown here. So that beta indicates how many of them got collected and that made up the collector current, and how many of them got recombined here into the base region, which form the base current. So usually it is a factor ranging from 50 to 100. So it is called as current gain. It's the ratio of collector current to the base current. So base current is pretty small, let's say 100 times or 50 times smaller than the collector current. Okay. Another parameter is called as alpha, which is called as common base current gain. So this configuration that we are seeing here is called as common base configuration. Why? Because the base is common to the emitter and the collector. Okay. In the common emitter configuration, we go for calculating the current gain. In the common base configuration, we go for calculating current gain, but that is alpha. So alpha is the ratio of IC over IE. It is saying that how much is the collector current and how much is your emitter current. So usually, let's say you have 100% of electrons and 90% of them reach to the collector region and 10% get lost during the recombination process with the in the whole region, in the p-type semiconductor. So the alpha would be 90 over 100. So it is 0.9. So usually the value of alpha ranges between 0.9 to 0.99. And it will be always less than 1. So that's why you can say that if you try to use this BJT in the common base configuration, you don't have a current gain larger than 1. Rather, it is less than 1. So you don't have any gain. You cannot amplify the signal to a higher level. But if you configure your transistor in a common emitter region where emitter will be common, for example, let's say you have this transistor N, P, N, and this is your emitter, this is your base, and this is your collector, and make the emitter common to the terminal like this. So you see now, again, the emitter base junction should be forward biased. So apply the positive voltage here and negative to the base. This is positive to the P and negative to the N. And for the collector base, make it reverse bias. So N gets positive and this emitter gets negative here. Okay, so you can say that this is a common emitter configuration in which your gain would be beta, and that would be about 50 to 100. So in this, you have a large amplification of the signal, and that's why you always use the BJT in a common emitter configuration if you want to use it as an amplifier for voltage gain amplification or current gain amplification. All right, so That was all about the BJT operations.